Hi, everyone. My name is Dan Milroy, and I'm here together with my colleague, Vanessa Sochat from the Lawrence Livermore National Laboratory. And we're going to be talking to you today about the future of discovery, combining converged computing with agentic science and the evolution of the HPC Center. And we're going to give you sets of slides on each of these concepts and hopefully tie them all together and also define what these are and provide you with some details. So, to start off, I want to highlight that we're really entering a crisis of complexity related to post-exascale at this point. So our science is really demanding orchestration together with automation and infrastructure. And when I say infrastructure, what I'm talking about is basically an explosion of complexity and also geographic diversity and distribution, together with increased heterogeneity and resources that change in time. So this is much more complex and changing environment than it used to be. And when I say used to be, I'm talking about kind of traditional HPC, how workloads tended to be expressed, how they were managed, versus what we're moving toward now is converged HPC, so cloud plus HPC technologies, where you're seeing HPC workloads that actually require cloud technologies, but also ways to manage HPC infrastructures that are more cloud-like, and then of course integrations of the cloud-like environments together into a seamless unit. And again, I'll get into a little bit more details on what that means, but in the context of the contrast between traditional HPC and where we see things going now, I want to highlight some different categories. The first is the workload itself. You're probably familiar with this. When we talk about traditional HPC workloads, we're thinking in general about monolithic batch simulations versus in a converged environment, what we're moving towards is a coupling of AI and ML together with simulations. So think of like MPI-based simulations and ensemble workflows or workloads that actually may include cloud-based services together. Now, the resource model for traditional HPC is focused on a static node-centric allocation. So think of things that are fixed. You count them in terms of the number of nodes. They don't change in time, et cetera. And the schedulers that supported these types of allocations tended to be schedulers that used static bitmaps, versus now we're moving toward a resource model in converged environments that is dynamic. It requires resource dynamism. It requires elasticity. And a lot of that is very well managed and modeled by resource graphs that represent resources plus the relationships between them and allows those to change in time. Now, in terms of management, traditional HPC, again, tends to be imperative. So think fixed configuration files and fixed job shapes. They're fixed because the human needs to define how they define their configurations and then also transitions between them via batch scripts or configuration files, and then how one job may relate to another, versus a converged HPC center is moving towards declarative management, where in this case, the human user is going to define the desired status and then allow the system to ensure that the current status aligns with and eventually changes into the human desired status. In terms of the interconnect, traditionally, there's a fixed administrator managed interconnect versus the converged HPC center, which is more cloud-like in the sense that it's user scoped and supports dynamic environments. Now, in terms of discovery, scientific discovery is becoming or used to rely on in traditional HPC environment modules and was very manual, versus converged HPC centers. What we're seeing is integrations for agentic discovery, and then also eventually perhaps fully autonomous discovery, or at least part of that will be fully autonomous. So you may have noticed that much of the different details and features I've listed in the above is driven by the workload manager. And in this case, what we're going to focus on throughout this talk is the Flux Framework and Kubernetes and various combinations between the two of those. So the Flux Framework is really up to the task. It's up to the task of post-exascale and the challenges related to that. Now, the Flux Framework is actually an advanced workload manager and resource orchestration suite, which is designed for modern, complex, and heterogeneous high-performance computing environments and also converged environments. Again, we'll get into that in a little bit. Furthermore, it's backed by a lot of expertise. Flux has over 25 contributors, including some of the principal engineers behind Slurm and developers with experience in container technology, scheduling, workflows, and cloud computing. And we also have dedicated researchers that work on this project. So more specifically, the Flux architecture addresses post-exascale challenges. It's designed to solve resource management challenges of this forthcoming era, and it bridges the gap between traditional batch processing and more modern dynamic workflows, some of the characteristics of which I described in one of the previous slides. Now, the NNSA exascale system El Capitan is currently the number one system on the top 500, and it is being scheduled exclusively by the Flux Framework. The Flux Framework is the only scheduler and resource manager that is running on the compute of El Capitan. Now, converged computing, so think of HPC and Kubernetes being brought together into a seamless environment. We're facilitating fully functional batch schedulers like Flux inside Kubernetes pods, and that also enables bypass of etcd bottlenecks via, for example, the Flux Operator. Again, you'll hear about this in a little bit. The Flux framework has support for complex and heterogeneous workflows. So these are workflows that are oriented or orientation towards coupling AI and ML together with traditional MPI-based simulations, which have to coexist and then share resources efficiently, kind of trade resources back and forth if necessary and change shape as necessary. There's also a need for graph-based resource models because that resource model, specifically a graph, handles complex hardware topologies, which ensures that the right job gets to the right hardware. So think of specific GPUs or interconnects for existing and future hardware. So even hardware that we haven't conceived of yet because directed graph is general enough to express various types of future resources and their relationships. Now, the Flux architecture also enables systems research and innovation via prototyping novel scheduling and queuing algorithms. Now, to give you a little bit more details on how the Flux architecture actually addresses post-exascale challenges, one of the features in particular that I want to highlight is hierarchical scheduling and resource management. Now, in this particular animation, what you can see is kind of a substrate layer, the darker blue layer, on two nodes, and those might be run by or managed by Slurm. It could be Flux itself, or it could be Kubernetes, or it could be another resource manager. And Flux can actually instantiate inside of those different resource managers and then create hierarchies of Flux where at least at each level of the hierarchy, the resources are subdivided such that the child inherits a subset or a subgraph of the resources, instantiates a separate tree-based overlay network, and also enabled specialization of how the resources are scheduled and managed. In other words, each one of the different layers of Flux and a Flux hierarchy can schedule and manage the resources differently, can use different scheduling policies, queuing policies, etc. And the huge advantage of this, well, actually there are several huge advantages, but two of them in particular are, one, it enables portability. So a workload can program to Flux and then this environment can be ported across many different infrastructures and run in exactly the same way. So you can encapsulate a workload in Flux, you can run it underneath Flux, or underneath Slurm, PBS, Kubernetes, etc., or LSF. Now, the other example or the other feature that this enables is actually increase in throughput by breaking traditional monolithic scheduler bottlenecks. So think of some of the difficulties of submitting a lot of jobs to Kubernetes, or I should say a lot of objects to Kubernetes and hitting the etcd or API server bottleneck. Now, the Flux framework is also designed to manage the complex and dynamic workloads required by, again, coupled AI and ML and simulation, so traditional HPC simulations. Now think of a workload that actually is going to change shape and resource requirements in time. Something that may start off with ML training, which requires GPUs, and then moves into a stage of one particular simulation that requires only CPUs, but that overlaps with another ML training job, which then, depending on the output of the training, may lead to the initialization of simulation B, which may require a different set of CPUs. And at that point, simulation A might stop. So you would ideally be able to remove or deallocate the resources that you're not using. So the traditional approach in HPC is to use static allocations, and this leads to underutilization of resources. In the Flux framework, we're designing this to support eventually, not quite yet, but eventually support all of the elasticity and dynamism that's needed by these type of workloads. So in terms of the Flux architecture's support for job specification, you can actually use a command line interface to request a number of nodes and number of processes that you need in much the same way as you would with a traditional HPC resource manager. But you can see that actually internally gets converted into something that's much more graph oriented. And that interfaces with the graph-based resource model, which actually enables native expression and control of complex topologies. What this looks like in a little more detail is the resource graph is something that, or the Flux uses a directed graph model, which enables sophisticated resource expression and job specification. So think in the previous slide where you had a command line interface that then resulted in a job specification that was graph-like, that actually ends up becoming translated into a graph-based job request, and that's matched against a directed graph of resources, and that is the graphical resource, the resource graph itself. And there are graph traversals that are done to actually ensure that the resources and the relationships match the request, and also that they're available at the times that are specified. Now, Flux, as I mentioned before, the Flux framework has support for converged computing, and that really is a best of both worlds that brings together cloud-native environments with HPC into its seamless whole. So it matches the needs of agentic and combined AI, ML, and MPI-based simulation workloads into one unit. And again, what we're really focusing on in converged computing here in this talk and in our work is bringing together the cloud-based features of Kubernetes. So think modularity, portability, automation, declarative management, together with kind of HPC characteristics, beneficial characteristics like high performance, support for low latency, sophisticated queuing and scheduling, and application or bulk application scale. So think MPI scale. Of course, at this point, cloud native scale is enormous as well and surpasses in most cases, or many cases, HPC scale. But the idea would be to bring these together into a best of both worlds environment. And we have several projects that exemplify this. The first is actually the Flux Operator, which runs seamlessly on both HPC, so bare metal, and cloud native and Kubernetes environments. So think of this as a way in which the Flux Operator, which based on the state that is defined by the user, reconciles that state and maintains it, as I said before, in a declarative manner. Now, in this case, what can actually happen is Kubernetes, or the operator, will actually lead to the creation of pods, and then Flux actually is instantiated in those pods and manages those pods in a hierarchical manner, exactly in the same way as if that they were bare metal. So you can have subdivision of resources, scheduler and resource management, specialization, etc. And the idea behind this, besides portability, is also to deploy HPC technologies in the cloud. And this, again, going back a few slides, gets around some of the bottlenecks that are related to the nature of Kubernetes, such as the API server and etcd. So think creation of many, many different Kubernetes objects simultaneously. So instead of creating individual jobs, you can create a Flux MiniCluster via the Flux Operator, and then submit thousands, tens of thousands, millions of jobs to that cluster without actually making requests for new objects in Kubernetes. Now, the second project that we have is user space Kubernetes and HPC together. So that's the bare metal bros. So in this case, we're actually deploying Kubernetes or user space Kubernetes with Flux on HPC environments. And this is really, again, getting the best of both worlds. So bringing together HPC simulations and services with AI and ML training, AI and ML software suites, et cetera, on HPC native environments. And in these environments, we've achieved pretty close to equal performance between bare metal and Kubernetes, user space Kubernetes, which include tests on AWS using the Elastic Fabric adapter, on Azure using InfiniBand, on Google Cloud with Ethernet, and on premises at Lawrence Livermore National Laboratory in the Corona cluster. Now I want to talk to you about some more infrastructure plans and how the Flux framework and kind of vision for the future can be used to support some of the initiatives that are coming out of the laboratory and also the federal government at this point. And what we're really trying to do is kind of change old thinking, which is how do we combine features from HPC and cloud, and how do we actually, with these features combined together, turn the entire center into something that's event-driven and an event-driven environment. So the United States has some initiatives that are seeking to accelerate scientific productivity through AI innovation. One of which you might have heard of is the Genesis mission. Again, that's a U.S. federal government initiative. There are also more specialized U.S. missions or initiatives such as the American Science Cloud, the Transformational AI Model Consortium, or ModCon. And then we also have something that is kind of more focused on some of the tri-labs and the national labs, and that's the Future Generation HPC Center, High Performance Computing Center. And the FG-HPCC, the Future Generation High Performance Computer Center, was a request for information, or RFI, that was put out by Lawrence Livermore National Laboratory for an HPC Center of the Future. And the timeline, we're talking instantiation around 2030, so in about 4 years or so, and it's going to be developed via a multi-vendor strategy, so combining multiple vendors together potentially. The requirements are a single unified kind of system or center that includes compute and facilitates access to compute, storage, and networking, and it requires performance of virtualization that is close to bare metal, features and support for secure enclaves and network isolation, cloud native management interfaces, cloud native control planes, and an open source software stack. So you can take a look at that initiative if you're interested in the link that I provided below. There's also several U.S. government initiatives or dedicated U.S. government initiatives. So there are coordinated national efforts to double scientific productivity within the decade through AI accelerated innovation. And think Genesis mission at this point. So you can see the U.S. federal government website on the Genesis mission, but there's, which actually integrates American Science and Security Platform across, or creates an American Science and Security Platform across the 17 national labs and the national lab system. It's going to support workflows which include fusion energy, nuclear modernization, national security, etc. There's also the American Science Cloud, or AMSC. That's a $40 million initiative and wants to create an environment of software and hardware with using AI to bring it together and create an AI-based science cloud. And finally, there's the Consortium. That's an AI model consortium, and that's about $30 million, and it's a foundation to create models for science. Kind of give you some example products or projects to consider as well. There's some current projects that are spanning the application to infrastructure space. The first one is Opal, or the Orchestrated Platform for Autonomous Laboratories, and that's actually using agents and robotic systems to manage AI experiments. So think, for example, gene discovery. There's IO Warp, which is a data management and project for data management and scientific workflows, or for scientific workflows, I should say. There's the Multi-Office Particle Accelerator team, and this supports or enables AI foundation models and intelligent assistance for particle accelerator teams. And finally, there's the Agentic Lab. That's a multi-agent setup for knowledge retrieval and protocol design specifically for organoid research. Now I want to hand off to Vanessa, and she's going to start talking about the rise of agentic workflows in science. Thank you.
An important part of this future vision is going to be agentic workflows in science. Now, before we talk about agentic workflows and how that might look, I want to tell you a little bit of my personal story and how I came to this particular opinion. Our team at the time had a very basic question. Can we take a large language model and ask it to convert a job specification? And so job specifications come in particular formats. What I'm showing you here are batch jobs. So in this case, we'd ask the LLM to convert a Slurm batch job into a Flux batch job. We were using on-premises models at the time. I, on my own, was using Gemini in the web interface. And it never occurred to me to ask Gemini to do this task. But I finally did, and this was captured in a conversation with one of my friends who then emailed me a year later a screenshot of our conversation. And I'm going to share that with you. So this email was titled very appropriately, "The Moment Vanessa Lost Her Mind Over LLMs." And indeed, this was the case. What I had done at the time is I had taken that job specification and I asked Gemini to convert it. But then I asked Gemini to convert it into an actual Flux canonical job spec, which is basically a JSON file. And I did it, and it worked, and it was almost perfect. And my response here, as you can see, is exactly my reaction. But this is very important for me because this captures the exact moment when I said, oh my goodness, this is going to be the future of so many things. And what more can we ask of these models? And so we started to think bigger. Forget about just one conversion. Let's ask the agents to do an entire scaling study. This means building the HPC application container from a Docker file, deploying it to Kubernetes, optimizing it for some figure of merit, and then actually running a scaling study across some sizes of nodes. And this is exactly what we did. We built a custom state machine orchestration tool where you would give it a plan. So that's a YAML file. The plan would be given to a manager. The manager and agent in and of itself would create different step agents, where a step agent is an expert at a particular task, like deploying a container, scaling, and each of those step agents would be allowed to use helper agents to debug errors or to parse a result. And when we put this all together, we ran it for 5 or 6 different HPC applications in different contexts, and we got really great results. I'll show you a few examples right now. So here's AMG and lamps. These are on the HPC 7G 16x large instances on AWS. Now the number of nodes is only 5 because at the time on AWS, we actually couldn't get very many nodes for instances. That was the best we could do. What you're looking at on the x-axis is the number of nodes. In green, we have the scaling efficiency, and then in blue is the figure of merit. The orange line represents ideal scaling. So that means that if we took the performance at one node and we extrapolated it out, how would it be if it was just perfect? So there's no CPU issues or there's no network. Well, the blue line represents that. That is the measured performance, and it's not perfect, but it did so well. And so this maybe isn't on par with a traditional HPC scaling study, but this is so good. And so we can take this little set of experiments that we did and bring it back to this larger question. How do agents fit in the future vision for the entire center? And what I want to propose to you today is not to get overwhelmed with this question, but to just think of individual tasks. And so let's walk through an example of that today, of running an HPC application. Let's start as the user, as the human, because that's what the role that we're familiar with. We look a little gingerbready. Let's give ourselves a little bit of swag. Alrighty, we're ready to run an HPC application. So the first thing that we're going to do is we are going to SSH into our cluster and we're going to build. We might use a tool like SPAC or EasyBuild. We might load environment modules and build from source, or maybe we'll build a container with Podman or Singularity. Once we have our application, we're going to write one of those batch scripts. It's going to define the resources that we need and the shape. It's going to export environment variables, and then we're going to run our application. Then we're going to give that script to the workload manager, and then we're probably going to watch the queue, make sure that it runs, monitor it, look at the result, parse the result, think about it, decide if we need to go back and rerun something. This is the entire manual process to do this. We're all very familiar with this. And so how do agents come in and kind of change this thinking? Well, what an agent can do, an agent can be given a task and it basically can perceive, plan, and accomplish goals, not just in like an hour, but over a long time horizon. So we're going to be gathering and interpreting data from scientific simulations. There's going to have to be some kind of API in there that empowers the agent to programmatically interact with our cluster in all the ways we just talked about. And a really cool future to think about is the fact that the foundational models that we use, they aren't going to be generic, they're going to be scientifically built. So a model that's really good at choosing parameters for lamps, for example. And this is going to be empowered. This is going to work with MCP. This is the Model Context Protocol. We are going to be building MCP servers that have tools, prompts, and resources that are going to carry out tasks. These are these API calls that we referenced above. Now, if you're kind of experienced in the space of APIs or you've been around a long time, you're probably scratching your head and you're like, what is so special about the idea of calling an API? Like, is there anything really that special about MCP? It just seems like it's an API server. I totally agree. This is the thought that I have had for quite a bit. I think what MCP solves is less of a technical problem and it's more of a cultural one. The fact that we finally have a reason to agree upon a common standard that we're all going to be calling tools in this particular way. And it's this AI ML explosion that has really driven centers to finally do that. And that's really great. So MCP, Model Context Protocol, there's kind of three buckets of things to think about. There are hosts. These are the user-facing applications. It might be a web interface. It might be a TUI, a terminal UI. It might be just a command line interface. The clients, that's the layer that's going to hold the session, interact with you, the user, but then also interact with APIs. And then the servers, these are the kind of the exposure of external capabilities of your cluster. This is where the API is running that will provide tasks and tools. We are going to be focusing on the server component because kind of that's the closest to HPC. Alrighty, so let's take what we just talked about, needing to build, needing to interact with the workload manager, and let's put it in the context of this MCP server. That means that we're going to have tools for our workload manager like Flux, tools for building, and then also other resources and prompts that are going to help us to use them. Now, if you were to kind of take that task and sit down, you would quickly have this question, wait a minute, where is this thing running? Because notably, you can bring up a little server on your laptop. You could bring it up in a job, but when you think about like a cluster, a center, you realize you're in an onion and there's all these different layers where you could deploy it, and maybe the answer isn't obvious. So let's talk a little bit about this. And I will also point out, as you probably know, that traditional HPC clusters are not oriented to hosting services. Just the concept of opening a port, depending on the center where you work, that is a process that can take many, many months of, security audits and discussions and permissions. It is not easy. So the first layer, or the first potential case where you can deploy this, is in the context of the batch job. And I'm going to argue that this is maybe one of the best choices. The reason being that you can deploy exactly the set of functions and tools that you need for your application, no more, no less. It comes up in the context of a job, your job runs, and then it comes down when you're done. And it's running as the user. There's no extended permissions or kind of translation of authorization. It's just very simple. Now, the next layer would be as a cluster service. So if your cluster has some kind of means to basically deploy a database or something for users, this would be that layer. And this use case might be, I need my group to share this MCP server. I need a long-running set of functions for a campaign that's going to last 6 months. The final kind of use case is as a multi-cluster service. So this use case is, okay, I actually have a tool that I want to call to figure out which cluster to submit the work to. And this is the hardest one because you're going to have to be receiving what comes down to kind of a webby looking request and then eventually map it to a user on a cluster. And I'm kind of alluding to this next part. There is actually a correlation between complexity and security. As we move up from the very simple case up to this multi-cluster level federated multi-user, you need more kind of security checks, more layers, and it's more complex. And these map, of course, to use cases. So what I want to suggest here is that choose the layer to deploy to based on your use case. And then, of course, you're going to have to figure out the complexity and then the security. For example, mapping a webby kind of token into LDAP or PAM. Okay, so what does this mean? Let's go back now to our workflow where we wanted to build an HPC application, run it with a workload manager, look at the result. What does this mean for an agentic framework? Well, an agentic framework is basically going to be some kind of orchestration with an LLM model, but how does that actually work? So first, I want to tell you about a talk that I really like. This is Andrej Karpathy. He gave this keynote. He was the director of AI at Tesla, then he was at OpenAI, and now I believe he has his own startup. He talked about software 1.0, 2.0, and now 3.0, and that 3.0 is conversational. And so that in and of itself is what an agentic framework is doing. It's basically moving a conversation between different contexts toward a common goal. And I won't tell you what software 1 and 2.0 are. Maybe you can guess. I really encourage you to watch this talk. And when you think about it, an agentic framework is really just a design philosophy. How do you take these steps in a workflow and string them together to call tools and to prompt LLMs? And in this context, you can think of the LM as the brain, and it's the brain that's being given a problem, has to reason through it, think about what tools to call, get feedback from the environment, from you, from the cluster about what the result was, and then keep going until it gets to a desired outcome. And that's basically it. These are the top two. So AutoGen and LangChain are kind of two well-known, accepted agentic frameworks. The third in this list is our state machine framework that we like to use. There are actually many others, but these are the three that we're focusing on now. So that entire manual user workflow that we talked about earlier, this basically becomes an interaction between that agentic framework that you chose and then your one or more MCP servers calling tools, getting feedback, making a decision about what to do next toward a desired outcome. For our particular use case, this is what it might look like. You're going to call a build prompt endpoint. A prompt endpoint is really just a templating endpoint where you're going to get back the prompt for the LLM. Maybe then you're going to do a spec build, generate a batch script, submit it to Flux, Flux status, which would be event-driven, and then analyze the result. And that's it. Here's the hard question, folks. Are we ready from a staffing perspective? There is a huge HPC, MCP skill gap that needs to be bridged. My gut feeling is no, but I think we can still get there. So here's just an example of some of the things we need to do. Asynchronous programming, if you've ever done JavaScript or async await patterns in Python, you've looked at this before. Event-driven architectures. So one really cool thing is that Flux Framework is event-driven. We're going to have to move away from kind of this polling architecture towards this. Kubernetes is also event-driven. If you've ever built a web application before, you're familiar with MVC, model view control. This is a design where you think about your model, which is the data and logic, the view, which is the user interface, and a web application that would be receiving request, giving back an HTML page, and then the control, the communication or interaction, that's the APIs. Modern API standards, a lot of us are probably familiar with these, maybe a little less so WebSockets. And then persistent service management. So not just running jobs or like a little database, but actually bringing something up maybe for a longer term running, being able to monitor it, health checks, that kind of thing. If you've used Kubernetes, you may have some familiarity with this. And then very important, but very hard is web security, or that's often referred to as Auth0. And then even harder, how that maps into traditional HPC authentication means. And here's kind of an insight, is that HPC, in order for us to really stay relevant and use a lot of these new technologies that are going to be so powerful for science, we must become more cloud-like in all of the layers of our stack. So here are some strategies to making that bridge, because we have to start somewhere, right? We're traditional HPC to more programmatic. Short term, start with the use cases that you have for your users. Pick specific tasks that you have or a user have. So for example, think about how you might deploy an MCP server in the context of a job for a specific application. If you already have some kind of cluster service architecture, you can start there. If you haven't looked at it, look at user space Kubernetes. You can have your cake and eat it too, have your orchestration and eat it too. Longer term, we need to think about the entire center as being programmatic event driven. This is the vision of the initiatives that we talked about earlier. My opinion is that converged computing and Kubernetes and the community with that is going to be immensely important for a successful outcome. And the hard thing to say is that we do not know what the future HPC center looks like. We have ideas, they're kind of a little bit blurry, but we are excited, we are curious, and we are going to find out, and we will get there. Caveat, I am not a sysadmin, so I can't give you good sysadmin advice, but I can tell you that I've sort of worked in emerging technologies and research computing, and I've done extensive cloud development and DevOps. And so I have quite a bit of breadth and depth in these areas to kind of think about this. Now, what is our team actively working on that we think is going to be very important for these next stages of work? The first is Flux integration with Kubeflow for AI ML and HPC simulation. We had a KEP that was merged, and we have our actual PR to add Flux to Kubeflow, which is done and will be discussed at a Kubeflow meeting this month. We are imagining and designing a Kubernetes operator for agentic workflows specific for HPC or science. We're taking a lot of the common things that we need to do for our workload manager Flux and just for HPC, and we're putting them into packages with functions that another user could easily deploy to a server or application. We are thinking about multi-cluster scheduling algorithms and infrastructure. And of course, there's FG-HPCC, which is focused at our lab. This is oriented for 2030. Challenges to work on. This is just the start of the list. So I don't need to read through these, but basically tool calling, giving back a single long list is maybe not the best way to do it. Multi-agentic, thinking about how two agents that weren't initially designed to work together actually could. Validation is always very challenging, and when do you bring in a human to kind of look at something? Guardrails, so an example guardrail is for our scaling study. We had an auto-scaling cluster. What was preventing that agent from deciding to scale that up to 1,000 nodes? Human interaction, how and when to bring in humans. Scheduling is really interesting, especially when you have multi-cluster, multi-objective, and you're choosing between heterogeneous resources. Identity is really hard because of that mapping between different spaces between, cloud identity management and then traditional HPC. And the ... is because there's more, and there's also challenges that we haven't even identified that are out there yet. So what are steps that you could take now? Think about it. What are problems that your users have? What are tasks that users have that could be agentic? How do you deploy an MCP server under a job? How would you do it today? And then maybe how would you like to do it in the future? Think of your tasks that you have as an administrator. What does it mean to be agentic? What larger community projects can be extended to the HPC community? How can we contribute? So this example would be Kubeflow. And then think about the hard questions. So think about security, think about permission. Make sure that you don't forget about these things as you're moving toward this agentic future. So in conclusion, the HPC center of the future is built upon convergence, modularity, and agency. We need hierarchical resource orchestration. A monolithic framework is not going to cut it anymore. We need something that supports modern, complex, heterogeneous workloads. User space orchestration and empowering users to get done what they need and not relying on you all the time is going to be immensely important. We need standard protocols. This has always sort of been a case. It's really cool that we're all kind of converging on MCP. Think of what it means for science to be AI-driven, a scientific AI agent. Take all the things that you need and turn them into tools that will empower people. Now, kind of a softer point is this idea that roles are changing. Your role in 2020 is absolutely not going to look like your role in 2030. And you need to be open to learning, curiosity, and the fact that it's going to be different, which is sometimes hard, Also, prototyping is cheap. Code used to be this really valuable asset, and it's totally not anymore. And so when you're working on something, make a bunch of prototypes, try out a bunch of ideas before you kind of settle on something. Learn a lot. Because the HPC center of the future is not just going to be this facility for running jobs. It is a proactive, autonomous platform that accelerates science. So thank you so much for having us today. We would love to take your questions and have more discussion.